Hello students, welcome to Narayan PU College online classes. In the last video, we have discussed about reactivity towards the halogens of the 15th group elements. In the first part, I already mentioned 15th group elements form two types of halides. One is trihalides and another one is pentahalides. Trihalides part we have already completed, and now it is pentahalides. Clear? Same what points we have discussed there in the trihalides, we will discuss the same. And you know that pentahalides, if I take, clear? So nitrogen, suppose if I take here phosphorus, E means what here? E is equal to, right here, E is equal to phosphorus, arsenic, antimony and bismuth. Clear? What is the X? X can be chlorine, fluorine, chlorine, fluorine, chlorine, bromine and iodine. Clear? So if you see here, what is the hybridization of central element in the pentahalides? Hybridization you have to take. Suppose if I take PCl5, clear? So this is chlorine and chlorine, here chlorine, there will be a chlorine and chlorine. This is PCl5. Clear? PCl5 means, and you know that phosphorus means what it is? 3s2, 3p3, and here you know 2 electrons here and there will be 3 electrons. This is the ground state electronic configuration, outermost. Clear? And you know, and phosphorus will have the empty d orbitals also, 5 d orbitals. If I write here first excited state, then what will happen here? One of this electron will entered into the d orbital, entered into the what it is, d orbital. Clear? It is d orbital. Now how many unpaired electrons are present here? 5 unpaired electrons. So that's why phosphorus form how many bonds here? 5 bonds. So that's why these unpaired electrons involved in the bond formation. So phosphorus will form here 5 bonds with the chlorine atoms, each chlorine atom. Clear? So that's why, is there any lone pair of electrons here? No. Previous year, see, if it is lone pair means it will form 3 bonds, but here 5 bonds means there is no lone pair of electrons. So that's why all are which one? Bond pairs only. How many bond pairs are there? 5. So that's why, what is the hybridization here? Hybridization you already know. What is the hybridization short formula? Hybridization to calculate, what is the formula? You know that number of bond pairs. What it is here? Hybridization. Number of bond pair plus number of free lone pairs. This is the formula. Clear? So how many bond pairs are there? 5. 5 plus. Is there any lone pair here? No, 0. So that's why what it is? 5. 5 means yes, and P 4, 1s P, and you will get the D. This is sp3d. That is the hybridization. Clear? So what is the first point here? What is the hybridization of central atom? Central atom hybridization. Central atom hybridization. What is the central atom hybridization? sp3d. Clear? In the pentahalides. And you know that, next point. And in this one, how many bond pairs are there? There will be 4 bond pairs and 0 lone pair. 5 bond pairs and 0 lone pairs means what is the shape of that molecule? You already studied in the chemical bonding. And trigonal bipyramidal shape. Bipyramidal shape. That is the molecule. So what is that trigonal bipyramidal means? Clear? If I write suppose the PCl5, the structure for the PCl5 if I write, and this is phosphorus here, and there will be a trigonal bipyramidal means I will write in this way. So there is a trigonal, clear? Phosphorus here, this is a triangle, trigonal bipyramids. These two are pyramids. Clear? So here chlorine, 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 chlorine and chlorine. And we will discuss about this structure in the means phosphorus halides are there. Next concept is there we will discuss. This is about the which one here? Central atom hybridization is sp3d, 3 bond pairs and trigonal bipyramids. And very important point here, have you observed here? I have written E is equal to phosphorus, arsenic, antimony and bismuth. I have not written nitrogen here, you see. Clear? Why? Why? Because you already know that nitrogen cannot form the pentahalides. Why nitrogen cannot form the pentahalides? To form a pentahalides, I have already written here, to form a pentahalides, D orbital means one of the electron. You see nitrogen, you already know. What is the nitrogen electronic configuration? ns2 np3. See here. And 2 electrons in the p orbital. How many electrons are there? There are 3 electrons. How many unpaired electrons are there here? 3. So nitrogen can form how many bonds? 3 bonds. To form, 5 bonds. And the next, if it is having D orbital, then one of this electron will jump in the first excited state. But you know that nitrogen does not have the D orbital. So that's why can it form the pentahalides? No, it cannot form the pentahalide. It can form up to the trihalides. It can form the trihalides but cannot form the pentahalides. That is important. Clear? So nitrogen, you know that here, nitrogen cannot form pentahalides. Cannot form pentahalides. Why? Because of absence of D orbital. Because of which one, ma? Because of absence of D orbitals. Absence of D orbital. D orbitals. This is one reason. Clear, ma? Next one. Next, if you are going next point here, bismuth has less tendency to form the pentahalides. Clear, ma? So why bismuth has less tendency to form the pentahalides? We have already discussed previous. If you are moving from the nitrogen to bismuth, clear, ma? And the bismuth can form the 3 bonds instead. Bismuth will form the 3 bonds instead of the 5 bonds. Why, ma? Because of inert pair effect. Have I mentioned or not? My inert pair effect is there. Due to the inert pair effect, that bismuth s orbitals are due to the poor shielding effect of the d and f orbital of the bismuth. Nuclear force on the s orbital will be high, so nucleus will hold the s electrons of the bismuth tightly. So that's why, and the only 3 electrons, p orbital 3 electrons only involved in the bond formation. Even though bismuth has the d orbital, but and due to the inert pair effect, only bismuth forms the 3 bonds. So that's why bismuth has less tendency to form pentahalides. Clear, ma? Less tendency to form pentahalides. Why? Because +5 oxidation state stability. I will write reason, because reason is here. What is the reason for this? Clear, ma? Because +5 oxidation state of +5 oxidation stability. Clear? Stability decreases down the group, or simply you can write the +5 oxidation state of the bismuth is less stable. +5 oxidation state of bismuth is less stable. Clear? So that is compared to the which one? +3 oxidation state. Clear? That you can write here, simple example. Clear? And next one, this is means nitrogen cannot form pentahalide. Bismuth has the capability but less tendency, because of nitrogen mainly forms the 3 bonds instead of the 5 bonds because of the inert pair effect. Clear? So that is, you simply write here +5 oxidation state of bismuth is less stable. Because why I am saying, if bismuth forms, suppose this is BiF5. Clear, ma? Then what is the oxidation state of the bismuth here? +5. If +5 oxidation state means, +5 oxidation stability decreases down the group. +5 oxidation stability decreases and +3 oxidation stability increases. So that's why bismuth has the lesser tendency to form the pentahalides. Clear, ma? So that is important point. And next one is here, pentahalides are covalent. Pentahalides are which one here? Covalent. You already know that. Pentahalides means, what is the oxidation state on the central atom? +5. Clear, no? Suppose if I write here PCl5, what is the oxidation state? +5 and here -1. Clear, no? So +5 oxidation state is there. Cation has the high means charge. Here P +5 and here 5 Cl-. Cation. cation has which charge ma? Highest charge. When cation is highest charge mean highly means high positive charge, then you know they form the mainly covalent compounds. I already said Fossen's rule. For covalent compounds, what are the main three Fossen's rule? Cation should be small, anion should be large, and charge should be high. If it is charge is high, and those compounds will form the mainly which one ma here? Covalent compounds. Clear ma? So that's why. And pentahalides are mainly covalents. Pentahalides are mainly covalent. Mainly covalent. Pentahalides are which one ma? Mainly covalent. Clear? And next one. And you know covalent character decreases down the group. Clear? You know that here. You know covalent character decreases down the group of the pentahalides. Clear ma here? Now next one, very very important here. Pentahalides are less stable than the trihalides. It is important. Clear ma here? Pentahalides are, you know, pentahalides are less stable than trihalides. What is the reasons here? Clear ma? Pentahalides are less stable compared to the what is ma? Trihalides. Clear ma? One is important, you know that here +5 oxidation state stability decreases the down the group. Clear ma? So if you are here and you know nitrogen and phosphorus, they may show the -3, +3 and +5, and nitrogen, phosphorus and arsenic also. Phosphorus if you take -3, +3 and +5. Arsenic, what is the oxidation state? It mainly shows +3 and +5. And you know antimony mainly shows the +3 and +5. Bismuth if you take, mainly it will show the +3. As you are moving from the nitrogen to phosphorus, +5 oxidation state stability decreases and +3 oxidation state stability increases. Means bismuth, it wants to be in the trihalides form only, not in the pentahalides form. If trihalides form means it is +3 oxidation state of the bismuth is more stable compared to the +5 oxidation state. So that why it wants to form always trihalides. In the trihalides only it is +3. So that's why one reason is here, as the down the group, you know that to form a 5 bonds here. Pentahalides means how many bonds it has to form? 5 bonds it has to form. But you know down the group inert pair effect increases. So that's why you know antimony and bismuth mainly form the, you know what it is ma? Trihalides only. So that's why stability of the pentahalides decreases and stability of the trihalides increases down the group. Clear? So that's why the main reason here, inert pair effect. One is increases inert pair effect down the group, and one is inert pair effect. This is the one important. That's why trihalides are more stable than the pentahalides. Clear? Another one reason is here. Steric hindrance increases. Steric hindrance. What is the steric hindrance you see? Clear? If I take suppose PCl5, how many chlorine atoms are there here? PCl5 total 5, and PCl3 means how many chlorine atoms are there? 3. You know these all are having pair of 3 chlorine is having 3 lone pair of electrons, and also these are bigger groups. Clear? So what will happen, you see, there will be a steric hindrance. When it is a steric hindrance is there will be a repulsions. When there are repulsions, the molecule become unstable. But if you take in the PCl3, you know, and you know they are away from each other, only 3 molecules are there, here 5 and here 3. So where the steric hindrance is more? Here. So that's why here repulsions will be more and here repulsions will be less. So that's why that is one of the reason pentahalides are less stable than the which one ma? Trihalides. Got my point ma here? So this is pentahalides are main reason, these two. Clear ma? So next point if I discuss, next one is Penta halides, you know, less stable, so that's why they easily undergo decomposition reactions. Clear na? If I take suppose one is example PCl5 and it is, you know, unstable, which one is stable? PCl3 is stable, so that's why it will decompose. If you just heat, you will get the PCl3 plus what you will get, ma? Cl2. You see ma here? PCl3 plus what it is, ma? Cl2. Clear? And you know PCl5 is a, this is important, PCl5 exists as a covalent compound, exists as a covalent compound in vapor phase. In which phase ma here? Vapor phase, means in the gaseous state. Clear ma here? In the same way, if I take here PCl5, it is existed as a ionic compound in the crystalline state. PCl5 exists as a ionic compound, in which state ma? In crystalline state. In which state ma here? Crystalline state. Clear ma? In the solid state. How it will be existed means, it will be existed in the ionic form. It existed as a ionic form. In which one ma? Crystalline state. Means one is PCl4 plus and another one is PCl6 minus. This is PCl5 only, and means it is in the dimeric, like you see PCl4 P2Cl10. Clear ma? It is dimeric form like PCl4 plus and PCl6 minus. Clear ma? So this is in the PCl5 exists as a ionic form. In which one? Crystalline state. But in the vapor phase, it is existed as a covalent compound. And sometimes this is important, very important. Sometimes they have given, previous they have given in the competitive examination also. Clear? So that's why. What is the hybridization here? Phosphorus and having how many bonds here? Phosphorus losing one electron. Clear no? Phosphorus means what it is? Phosphorus belongs to which group? Fifth group. Fifth group means phosphorus having positive one charge means remove one electron. Remove one electron, one chlorine means these electrons involved in the bond formation with the chlorine. So that's why how many bond pair electrons are? 4. 4 plus 0 means what is the hybridization here? sp3. And what is the hybridization here? 6 electrons are there. You know phosphorus, what is the group number? 5. But phosphorus is having which one? Negative charge. Negative charge means you add one electron. How many chlorines are there? 6 chlorine. Each chlorine give one electron. These are phosphorus electrons. Now each of chlorine will give one electron and make a bond here. So how many bonds it will form? 6 bonds. So is there any lone pair of electrons here? No, all are bond pair. How many bond pairs? 6. 6 means what is ma? sp3d2. sp3d2 means what is the sp3 means? You know 4 0. Bond pairs how many ma here? 4 bond pairs and 0 lone pair. And here how many? 6 bond pairs and here how many lone pairs? 0 lone pairs. 0 lone pairs. So what is the shape of this PCl4? 4 0 means what it is ma? Tetrahedral. What it is ma here? Tetrahedral. PCl6 shape what it is? Octahedral. Clear ma? Say this is. So this is and how this PCl5 existed as a means in the crystalline state it is existed as a PCl4 plus and PCl6 minus. Here 4 bonds are there. Clear ma? 4 bonds are there and lone pair is also used. So that's why here there is no free lone pair. So 4 bond pairs and 0 lone pairs. So that's why what is the shape of this molecule? Tetrahedral and here octahedral. 6 bond pairs and lone pairs. Clear ma? And the next one and remaining, you know, phosphorus, bromide, and they are also existed in the ionic form. PBr5 can also, Pi5 can also exist in ionic form like PBrO4 plus and what it is ma here? Br minus. In the same way Pi5 also existed as a, you know, ionic form in the crystalline. Clear ma? I minus. Clear ma? So this is next point. And last point here in the phosphorus pentahalides are, you know, phosphorus pentahalides, not phosphorus, pentahalides. Pentahalides of 15th group elements act as a Lewis acids. Act as a which one here? Lewis acids. Why? Because they have empty d orbital. Empty d orbital means if you want anyone is giving electron, suppose you take here pf5 plus if any f1 minus is giving electron, so phosphorus can form how many bonds here? Maximum 5 bonds. If they involved means SR electrons also involved in the bond formation. You know, here there are 2 electrons and here 3 electrons are there with the phosphorus. But d orbitals are there with the phosphorus. There are d orbital. One of electron will jump here. How many bonds it will form? You know, 5 bonds. But to form a 6 bond, phosphorus doesn't have electron, but having which orbital? Empty d orbital. So that's why it give electrons to empty d orbital and make a coordinate bond. So that's why here you will get the compound is pF6 minus. Clear ma? So these molecules having the d orbital, so that's why they can accept the electron. If the electron acceptor, we will call it as a Lewis acid. And this is about, clear ma? So this is about, and what it is ma here? About the phosphorus means Penta Halides of the 15th group elements. Clear ma? So now we have discussed about the reactivity, 15th group elements reactivity towards the hydrogen, oxygen and halogen. Clear ma? Next concept is here dinitrogen, and dinitrogen means what is ma? N2. Clear? So how we will prepare, and preparations we will see, and after then physical properties, chemical properties and then uses. This is the concept. Clear ma? Commercial preparation of dinitrogen. How dinitrogen is commercially prepared? It is simple. So it is a commercially it is prepared by the liquefaction and distillation of air. Clear ma? In the air, you know, 78% of nitrogen is available in the by volume in the atmosphere. Clear ma? So from that one, how commercially it is prepared means it is commercially prepared by a liquefaction and distillation. Liquefaction and what it is ma here? A distillation of air or distillation from air. Clear ma? So you know that here in this case, you know, mainly in the air oxygen is present and nitrogen is present. Majorly means 21% of oxygen and 78% of nitrogen. Means if we liquefy and distillation, liquefy means we have to air, you know, they are in the form of gaseous phase, we have to convert that one into the liquid phase. Then liquefaction, then distillation. Distillation means we have oxygen is there and nitrogen, we have to separate both. Clear ma? And now if you do the distillation, clear ma? First one, nitrogen N2 distill out first and leaving behind liquid nitrogen. This is what it is ma here. You have to write liquid nitrogen distill out first, leaving behind liquid oxygen. Why? Because means, and you know, this liquid nitrogen will have low boiling point compared to the liquid oxygen. Liquid oxygen boiling point is 90 Kelvin and this boiling point, liquid nitrogen boiling point is 77.2 Kelvin, which is having low boiling point, that will be distilled out first. Clear? So that's why nitrogen will distill out and in the liquid mixture nitrogen will be left. So this is commercial preparation of dinitrogen. Clear? Next one, and this is first preparation. Clear here? Next one, put the heading here. First one, preparations. Put the, what is the first one heading here? Preparation methods of N2. This is the heading. In that one, first method is commercial preparation and the second one is laboratory preparation. How we will prepare dinitrogen in the laboratory? Clear ma? So how we will prepare means, first of all, and we will heat the mixture of ammonium chloride and sodium nitrite. What it is here? Ammonium chloride, sodium, you know, nitrite. sodium nitrite, and then what you will get, you see, NaCl will be removed, then you will get ammonium nitrite minus NaCl. What you will get here? You got here ammonium nitrite, and this ammonium nitrite, if you heat, further heating, then what, this is main compound, clear ma? Then what happened, you see, 2 oxygens and 4 hydrogens will be removed as a 2H2O, clear ma? Then what left here, N and N, you will get the nitrogen. This is, so this is preparation of which one here, laboratory preparation. It is commercial preparation. Commercial preparation means by from the atmosphere or from the air, and laboratory preparation means first ammonium chloride treated with the what it is here, sodium nitrite, and gives the ammonium nitrite, further heating will produce nitrogen gas, clear ma? Next one, what is the third preparation? Third preparation is, and from ammonium dichromate, from which one here, ammonium, from ammonium dichromate, from ammonium dichromate. What is the ammonium dichromate formula here? Potassium dichromate you already know, K2Cr2O7, instead of that ammonium should be there, NH4, that is ammonium dichromate. And from this, thermal decomposition of ammonium dichromate, what it is here, thermal decomposition means take the ammonium dichromate and heat it. This is we will call as a thermal decomposition. Thermal decomposition of ammonium dichromate produces nitrogen gas, clear ma? So now you see what happens here, and CrO7 will be converted into Cr2O3. First one, what it is ma, Cr2O7, and here ammonium it is there, Cr2O3 will be, it will be converted into Cr2O3. How many oxygens are removed here? 3. How many are there here? 4. 4 means, and oxygens and here hydrogens will be removed as a water. So that's why next one, what it is ma, water. Clear ma? So how many oxygens are there here? 4 oxygens, and then you know next one, what is there? Cr2O3 is removed, remaining oxygens and hydrogens will be removed as a water. Next what is there? N2 is there, that is only, and this is N2, clear ma? Then balance here, and 3 oxygens are there and 7, and here 4 should be there, means you have to multiply this one with the 4. 4 into 2 8, and 2 into 8 8, that is preparation of what it is ma here, nitrogen from the ammonium, what it is ma here, dichromate. And the next preparation here, fourth one is same, from barium azides, from what it is ma here, barium, from barium azides, from barium azides, clear ma? You know that barium azides, or you can take sodium azide also. Thermal decomposition, same, thermal decomposition of azides produces the, just heat it, clear ma? Barium azide. If you heat this compound, then you will get the, you know, nitrogen. Take the here barium plus what you will get ma, nitrogen, clear? So now you know that here barium nitrogens are 3 and here 2. I will multiply this one with the 2 and I will multiply this one with the 3. Then 2 into 3 6, and 3 nitrogen 6, and 2 barium, clear ma? So these are the what it is ma, preparations of nitrogens from the different methods. One is commercial preparation, laboratory preparation from ammonium dichromate and barium azides, clear? So we have already discussed about the preparation methods of dinitrogen. Now physical properties, clear ma? So what are the physical properties here? It is a colorless, nitrogen, you know, nitrogen gas is a colorless and also tasteless, odorless, non-toxic gas. It is non-toxic, clear? Because it is available in the atmosphere. If it is toxic, you know, so we cannot live on the earth, clear? So that's why it is a colorless, tasteless, odorless and non-toxic gas, and it has mainly 2 stable isotopes, clear ma? One is 7 nitrogen 14 and 7 nitrogen 15, clear ma? So here isotopes means you already know, having the same atomic number and different mass number. These 2 isotopes are stable for the of the nitrogen. And third one is, it is very slightly soluble in water. you know, oxygen, it is soluble in water, but it is very slightly soluble in water. And next one is it has low freezing point 63.2 and also very low boiling point. So that's why when we have extracted from the when we distilled liquid nitrogen and oxygen, liquid nitrogen distilled out first. Why? Because it is having very low boiling point compared to the liquid oxygen, and it is observed on the activated charcoal. And this is about the physical properties of dinitrogen. Then we will go for chemical properties. So now chemical properties. So I already discussed in the previous, nitrogen is almost, it is inert. Clear ma? So nitrogen gas, why it is inert? Because you know, between the two nitrogen atom triple bond is existed. So that's why to involve nitrogen in the reactions, first the triple bond should be broken. So that's why, and breaking of the triple bond is required high amount of heat energy. So that's why, and at room temperature nitrogen is a, you know, it is inert. Nitrogen is inert. Nitrogen is inert at where ma? Room temperature. Clear? But you know, and reactivity increases with the increase in temperature. Clear ma? So reactivity of nitrogen increases, reactivity of nitrogen increases, reactivity of nitrogen increases with rise in temperature. Rise in what it is ma here? Temperature. As the temperature increases, you know, and the double bond, triple bond between the nitrogen atom slowly breaks, then they involved in the reaction. So that's why reactivity of nitrogen increases with rise in temperature. Clear? Now it will react, nitrogen will react with metals and non-metals also at high temperature. Clear? So first one is reaction with metals. Clear? So first one is reaction with metals. Clear? So you know that whenever nitrogen, clear ma? Whenever nitrogen react with metal, metal gives metal nitrides. What it will give ma here? Metal nitrides. Clear? And we have already discussed, see, first one, lithium plus nitrogen at very high temperature. What you will get ma? Lithium nitride, Li3N2, lithium nitride, balance here 3 nitrogen atom. And in the same way magnesium, magnesium plus, you know what it is ma here? Nitrogen, you will get here Li3N, this is. Clear ma? Suppose if I take lithium and nitrogen, nitrogen is 3, lithium is 1, so Li3N you will get. Clear ma? Li3N means I have to take here 2 nitrogen atoms are there, multiply with the 2, then I will get the 6. Now it is balanced. Clear ma? With the magnesium you will get the magnesium nitride. We have already discussed, this is nitrides you will get. This is balance here 3 magnesium. In the same way, whenever it is reacted with the aluminum, clear ma? Aluminum, what you will get here? Aln. Why you will get like this? You know, aluminum and nitrogen, valence of aluminum is 3, nitrogen also 3. Crisscross method you do, you will get Al3N3. Al3N3 means what we can write ma? Aln. So 2 nitrogens, and here you will get the 2. So what you are getting here? You are getting metal nitrides. What is the metal nitride? Lithium nitride, magnesium nitride, aluminum nitride. Clear ma? So next one is, this is reaction with metals. Now reaction with non-metals. Reaction with non-metals. Clear ma? Reaction with non-metals. Clear? First of all, reaction with hydrogen. Non-metals means what it is ma? Reaction with, suppose if I take hydrogen, reaction with what it is ma here? Hydrogen. Clear? So you know that nitrogen react with the hydrogen and produces, you know, ammonia. N2 plus H2, you will get NH3. Clear ma? So here balance N2 plus H2, you will get NH3. 3 are there and I will put this one with the 3 and it will multiply with the 2. Then 3 into 2 6, 2 into 3 6 and 2 nitrogen atoms are there. And this you see, whenever nitrogen reacted with the hydrogen, what you are getting ma? Ammonia. You are getting ammonia. Clear? But you have to maintain here 700 Kelvin temperature and 200 atmosphere and catalyst, all that we will discuss in the next class, because preparation of NH3 is there. Clear? So this is one of the preparation and ammonia you are getting. This process we will call as a Haber's process. What it is ma here? Haber's process. Preparation of ammonia from the nitrogen and hydrogen in the presence of 700 degree Kelvin and 200 atmosphere, iron oxide catalyst, all it will come later, and this process we will call as a Haber process. And the second one, you know, reaction with oxygen. Reaction with what it is ma here? Oxygen. Clear? So reaction with oxygen, what the compound you will get? Nitrogen and oxygen are reacted at very high temperature, 2000 Kelvin temperature, you will get the NO. What is the NO ma here? Nitric oxide. This is what we will call ma, this is nitric oxide. Clear? And the next one, this is first reaction is reaction with what it is ma here? Metal, and the second one is reaction with non-metal, and third one is reaction with alumina. Reaction with what it is ma here? Alumina in presence of carbon. In presence of which one ma here? Carbon. This is third reaction. Clear? Simple. When we treated this nitrogen with the alumina, what is the formula of alumina? Al2O3. Alumina. Clear ma? And plus in presence of which one ma? Carbon. Clear? You know that nitrogen and aluminum will form the aluminum nitride. Clear ma? So you will get Aln, how many moles here? 2 moles plus, and carbon and oxygen will be removed as a carbon monoxide. Here 3 oxygens are there, so that's why I put here 3 oxygens, and how many carbons I have to put here? 3 carbons. So what you are getting here? Aluminium nitride. Aluminium, what it is ma here? Nitride. Clear ma? So this is third one. Next, fourth reaction. So what is the fourth reaction here? Is reaction with calcium carbide. What is the fourth reaction ma here? Reaction with calcium carbide, CaC2. CaC2. What is this name? Calcium carbide. This is calcium carbide. This is clear ma? Reaction with calcium carbide. Clear? So what is this reaction? Clear? So now nitrogen, whenever nitrogen is reacted with calcium carbide, clear ma? You will get the compound is calcium cyanamide plus carbon. What is the name of this compound ma? Calcium cyanamide. Calcium, what it is ma here? Cyanamide. Clear? Plus what we are getting here? Carbon. Very important. This calcium cyanamide and carbon. Carbon means coke. That mixture we will called as nitrolim. This question is asked in the competitive examination. Calcium cyanamide plus coke. Coke means what it is ma? Carbon. Mixture we will called as a nitrolim. This is used as fertilizer. It is used as what it is ma? Fertilizer. Clear? And now if you take this calcium cyanamide and do the hydrolysis here, you will get ammonia. What you will get ma here? Ammonia plus calcium carbonate. See ma here? So here nitrogens, how many are there? 2. Means I have to multiply this equation with what it is ma? 2. Then how many oxygens, hydrogens are there? 6. 6 means I have to multiply this one with the 3. 3 means you see now it is nitrogen and this is will be removed as a ammonia. Nitrogen and hydrogen will be removed as a ammonia. Calcium, carbon and 3 oxygens are there. That is CaCO3, calcium carbonate. Clear ma? So this is about the chemical reactions of what it is ma? Nitrogen. So we have completed preparations of dinitrogen, physical properties and chemical reactions, chemical properties, and final one is uses of dinitrogen. Clear ma? So it is used in the manufacture of ammonia Haber process, I already mentioned, and we will discuss this one in the next coming classes, how to prepare the nitric acid by using dinitrogen. And you know, next calcium cyanamide, I already mentioned, calcium cyanamide plus coke we will call as a nitroleum, and all these compounds are mainly prepared from the what it is ma? Nitrogen, and it provides the inert atmosphere in the iron and steel industry. Clear? So nitrogen will not, it is a inert at room temperature, so that's why sometimes it required inert atmosphere for the preparation of some metals like iron and steel. So, and this inert atmosphere is used in the iron and steel industry, and it is also used as a refrigerant to preserve the biological materials, food items, and in cryosurgery. Clear ma? And nitrogen gas filled thermometers are used for the measuring the high temperature, and that thermometer is filled with the nitrogen gas, because the nitrogen gas, you know, it is unreactive, so it will be filled in the high temperature thermometers, and these are the uses of dinitrogen. And now this dinitrogen preparation, properties and uses are completed, and next we will start the ammonia.